enough of that elastic deformation that we need for energy harvesting. Okay, so those are kind of some of the important lessons here that we can get from that nonlinear model. I mean, basically the bottom line is like kind of what I want to kind of communicate is that these, a lot of these kind of principles and then modeling tools in nonlinear elasticity are going to be very important kind of as we kind of more and more enter the space of soft robotics, and then we start using these fluids and elastomers that undergo very large elastic deformation. Okay, so that's work with actuators. I kind of want to kind of change gears here, kind of put aside some of that modeling stuff and kind of focus a little bit more at a higher level in terms of different paradigms or approaches to very soft and stretchable circuits for our electronics and sensing. Okay, so a few kind of approaches right now, kind of I'd say probably the most mature are weighted electronics. Okay, so I mean you're probably mostly familiar with this from the work out of University of Illinois, Northwestern, introducing stretchability through wavy patterns, buckling, through meshes, serpentine shape. So this is great for achieving kind of stretchable functionality using kind of conventional electronic materials. One disadvantage of this is that you only get stretchability in the directions that you design. Okay, so these are not scalable in the sense that there are length scales, which of course these devices are not stretchable, and they're also not isotropic. Okay, and then kind of the third limitation, and I mean, this I guess depends on kind of the scale of your research program, is that these are can be very challenging to make and to integrate into other soft systems. Okay, if you wanted to scale this up, I mean, eventually you would need like multi-billion-dollar fab labs, for the types of materials that we're using here. But nonetheless, still, I mean, a very kind of I would say at this point, fairly kind of mature approach to